Great. Hi, my name is Lita, and this is hosting Nino, and we both work at Lyft. It's a ride-sharing platform that's only based out of the US and Canada right now, and we both work on the networking team. Um, we've and our network, the goal of the networking team is to uh, building software that makes the network easy to use and reliable, such that product engineers don't need to worry about connection handling or retries. Like we take care of that for you, and they just focus on their business logic. Um, so today I'm here to talk to you about a migration story and basically our migration over from our legacy VM infrastructure to Kubernetes. And we're gonna go over all of like a high level of what Kubernetes is, the service discovery, and Envoy, and so service mesh. However, the point of this talk is not all those little details, but the point of the talk is to pass along the framework and the concepts that we use during this migration process in order to still stay reliable and make it as painless as possible for our customers, our product engineers, and hopefully you would take these concepts with you to your next migration. So we've broken up this talk in three parts. The first is the why. So why are we doing this migration? Migrations are really expensive, and the bigger they are, the more engineering resources and expensive it is. Lyft is a hyper-growth company, and we have a lot of fierce competitors, and we haven't even won the market just yet. And so the fact that we're spending time to migrate this infrastructure versus building out features means there has to be a really good business reason for us to do this. Next is we'll go into the how of this migration, like what is our migration plan, and what are the values and the end state that we want to be in, and how we're going to get there. And so we'll dive into that story and how we're going to in our rollout plan and how we're going to go through this migration. And lastly, we'll explain our learnings from this migration. So as we're going along, what were the setbacks? What were the essential things we needed for this migration to be successful? And these are the pieces we hope that you could take with you so that you don't have to relearn them. So let's quickly dive into what Kubernetes is. Are people familiar with Kubernetes at all? Cool, there's some of you, so this is great. Okay, it's a big system. There's a lot of talks out there, but I'll give a pretty high level. Ultimately, Kubernetes is a container orchestrator, and it is a system that automates your deployments, automates your scaling, as well as manages your containers. It provides a set of APIs and resource definitions such that you can customize your deployments and customize your scale-up policies. What's powerful about Kubernetes and containers is that containers uses software virtualization to bake in all the dependencies, such as your operating system and all the software that you need to launch your application, such that when you start your container, it starts up right away. And with Kubernetes paired with containers, the idea is that it's first highly configurable, but also really quick to scale up. So the idea is that you could start your application, many instances of your application very quickly. So in order to give a context of why we decided to go with this migration, I wanted to provide a real business example. So back in 2017, there was a very popular boxing match that was aired on HBO, the Mayweather and McGregor fight. It was aired nationwide, and it was $100 for people to watch on HBO. And what people tended to do was congregate in friends' houses or bars in order to see it. And it actually hit record ratings, matching almost the Super Bowl, which is the highest sporting event in America. And so if you look at this moment here, after the match, everyone decided to go home all at the same time after the match was over. And unfortunately, so Lyft is actually really good about using historical data. It's a very real-time system, but we use historical data to predict capacity. So New Year's or certain recurring music events, we are able to account for that and scale accordingly. However, this was a one-off thing, and we can't predict every single event that's going to be super popular. So unfortunately, we did not prepare for this. And there was a few moments in time where we were degraded briefly. But in the business case, we don't want to be degraded when this happens. We want to be adaptive, and we want to be able to handle unexpected load because it's great for the business. So your question, like, why couldn't we just scale up? Like, that should be simple as that. Unfortunately, with the old infrastructure, it takes around 15 to 20 minutes to scale up, mostly because you still have to install Ubuntu, you have to install all these dependencies, and to launch a new instance, it takes that long. With Kubernetes, with containers, they offered scaling up instantly, and if you see their other Kubernetes talks, you could see the scale up being immediate, which is pretty impressive, like in a few seconds, which is very impressive. So that was one major reason to move to Kubernetes. Secondly is the separation of concerns. So the fact that right now the product engineer maintains all the orchestration YAML files in their service. Infrastructure provides a template and API, but for the most part, the product engineer needs to decide what kind of AWS instance they need, what kind of what kind of logic I need to start up my container, and then also, your machine, and what is the configuration for my security groups and logging. And so their job is to maintain all of that, and they don't want to worry about that. They just want to write application logic and business code, and they only touch this when a new service starts up or once a quarter for when they need to upgrade and account for their growth. So Kubernetes, you abstract all of that. You just configure how much CPU you need and how much memory you need, and what your scaling policy would be, how much batches of how much scaling you want to increase by. And so you cut all that concern in half, and they don't have to worry about what kind of cloud provider they need to learn. It's just they just need to understand how much CPU they need and how much memory they need, and it all just works through the Kubernetes APIs templates. Lastly, is the biggest thing is the immutable infrastructure. So when you launch a Kubernetes container, that container cannot be changed. And currently in our legacy infrastructure, we do an in-place swap. So because if we were to do a full rotation, it would take forever due to the fact that launching an instance takes so long. So that means that your code gets updated, but if you change anything in your orchestration, you can't really test it unless you term a box and watch it come up, or do a scaling event. And most people don't tend to do that, so because it takes so long. So there could be times where it could be very scary, where you realize you messed up your orchestration configuration, and you get paged in the middle of the night because you can't scale up. And that's a very scary situation to be in. With Kubernetes, there's none of that. When you deploy as the same as you would scale up due to the immutability. And that's also easier for infrastructures to reason about.
All right, so Lita took us through the first step of the framework. Why is it that we're going to spend all of these resources in this very expensive migration? We need to justify that, and justify that not only with technological decisions, but also with business reasons for going onto a new system. The second step that we used in our framework is the how. And these are the type of questions that we use when we're thinking about the how of our system. We first start with, what are the tools that we have at our disposition, or what are the tools that we need to build in order to go through this migration? Second, what does the current system actually look like? What are the trade-offs that we have historically made to get us to this place? Because that will inform how we get to where we want to be. Third, what are the goals that we're trying to accomplish? And this is different from the why. The why hopefully gives you justification for doing the migration, but the goals are actually giving you the optimizations that you're going to go forward with in order to get to your end state. And lastly, once you've answered these questions, you can actually go with your colleagues and go to the drawing board and say, okay, this is the system that we're going to get to, and these are the milestones that are going to get us there. So let's first start with this particular story. What are the tools that we had at our disposal to get this migration done, at least from the networking perspective? So the first tool, and perhaps the most important, is Envoy. And Envoy is a network proxy that was written and open sourced by Lyft It's similar to other proxies that you might have heard about, like Nginx and HA proxy. And really, it's a very flexible proxy, so it can be run standalone at the edge of your infrastructure as a front proxy, but it also can be run next side to side with your applications as a sidecar that is taking all the concerns of the network away from application engineers. Third is API configurable. What this allows you to do is to separate the concern from the operation of the network proxy from the configuration of the network proxy. So it allows us to build smart and robust systems that are actually independently configuring the proxy from the operation of the network. And so what this tool allows us to do is to have a common substrate at the network layer for both network behavior and also resilience. So let's look at Lyft's network topology today. And what you'll notice right away is that Envoy is everywhere. It really has become the universal network primitive that allows us to have the same common substrate along all parts of our infrastructure for network. All the way from the left, where you can see a mobile phone that is making a request into Lyft infrastructure by our users, be it drivers or riders. Those requests come in through to Lyft's infrastructure via front Envoy, which is the edge proxy that terminates requests at the edge of Lyft's infrastructure. And then those requests move on to the internal services. These are the actual services that Lyft product engineers have built to develop the platform that is Lyft and develop the business features that we want to have. And all the way through to third-party services like Stripe, which is our payments platform, or even our databases. What we want to focus on today is the internal services. These are the parts of our infrastructure that we're going to physically change from virtual machines to Kubernetes-based infrastructure. And what Envoy allows us to do is to build a mesh of these services. So regardless of if your service is written in Java or Python or Go, the network is handled by the same common substrate. So for example, here we have locations, which Lyft is service run in Python, and it handles the location of our drivers and our riders. But all the network requests flow into the service from via Envoy and flow out of the service via Envoy. All right, so now that we have some sense of the tools and the state of the system before, let's start with the concepts that we're going to use in order to make this migration possible from the networking layer. And the main concept that we're going to use here is service discovery. Service discovery is what actually pairs physical infrastructure, so in this case, IP addresses, with the logical business services that Lyft engineers have created. So for example, here on the left, we have a service that is written in Python, and it might have n number of machines, but really it's all one logical service. And what Envoy needs to be able to do is to discover what IPs are linked to what services in order for the network proxy to actually route requests to where they need to go. All right, so how does our service discovery infrastructure look like previous to Kubernetes? Well, we have different services all running Envoy, running in virtual machines, and they register their IPs, their IP service pair over with the discovery service, which is written in Python and backed by DynamoDB, but it can be backed by any database. And then every 30 seconds, the discovery service is delivering those IP service pairs over to the internal services. And this is what allows us to link IP addresses to services. So what is the desired end state that we have as we move on through this migration? What we want from the network layer is to be able to, regardless of if the physical infrastructure is only in Kubernetes, only in AWS, or maybe there's a service that is migrating and actively has physical resources in both places, we want to have a homogeneous view of the network. We want Envoy to be able to route requests regardless of where the physical infrastructure is. So now we have the tools, now we have what is our desired end state, and we have assessed what our current infrastructure looks like. Let's design some goals for this migration. So what we really want to do here is to enable our infrastructure team to keep Kubernetes accessible and easy to use for all the product engineers at Lyft that are building business logic, but at the same time, we want to keep Lyft reliable. As Lita say, Lyft is a business that is very time sensitive, and any blip in reliability can be hugely detrimental to the business. So that's the overarching goal. Let's look at some of the specific goals that we had for this migration. First, we wanted this migration to be a transparent change for product engineers. What this means is we're spending energy, we're spending resources in this migration. The last thing we want to do is to decrease the productivity of engineers that are building features that make Lyft more competitive. So we want this migration to be zero touch for them. That means they don't have to be aware of the underlying infrastructure to be able to keep doing their day-to-day job. Second, we want to have an incremental rollout of our infrastructure. And this plays two important roles. The first role is that you want to show wins real fast. You want to show how the changes that you're making to the infrastructure are improving the business. And so you want to have very small milestones that are showing that those wins incrementally. And the second reason we want to do an incremental rollout is because the last thing you want to do is to put something new out in your infrastructure and just bring the entire business down. So by doing incremental rollouts, we're managing that risk. And hand in hand with that goes the ability to roll back. So we're all humans, we all make mistakes. And even though we've put so much thought into this migration, there might be corner cases or edge cases that we didn't foresee. So we need to preserve the ability to have escape hatch and go back to the previous well-known state.
Okay, so now that you have a good idea of what our current legacy discovery system looks like, let's go into our actual migration plan. So hit next. So in the Kubernetes world, we have many Kubernetes clusters, and then services sharded amongst those clusters. And the idea of that is if like one cluster were to go down, that's okay. We can still route traffic to the other clusters and Lyft will still be up. A pod is a unit, it's equivalent to our like AWS instance or AWS machine. So like a pod is just like a workload, and services can be composed of many pods. And we have a Kubernetes API server, which is an etcd node that keeps tabs on what the state of that cluster is. So each cluster has an API server, and that keeps track of how many pods there are, and it emits events of when a new pod is created, or a pod is deleted, or updated. And then we have this control plane. So we migrated over from our Python discovery service to this control plane, which is written in Go. And that was because we needed more concurrency to send data to all the sidecar envoys. And we wanted to use gRPC and streaming protocols to send that data faster, especially in the Kubernetes world. Everything happens much faster than in our legacy world. And so the idea is that all the data gets slurped up both from the polling from the discovery service and through the watch APIs that Kubernetes provides. We get real-time events of pods coming up and spinning down, and then the control plane takes all that data, munges it all together, and converts them to Envoy configuration discovery data, and that gets sent out to all the sidecar envoys as a list of IP addresses. And the envoys don't really care if it's Kubernetes or if it's legacy. They just get a list of IP addresses to a logical service name, and thus traffic gets routed evenly amongst that list. So let's say you're like rolling out a service, a Python service, and you're trying to migrate over to Kubernetes. You could incrementally like increase the workload into Kubernetes, and then decrease the workload in legacy, such that like your traffic is ratioed based upon the amount of pods versus the amount of machines you have in our legacy infrastructure. And that way you can slowly migrate over, watching the stats that you care about, either it's business stats or network stats, like 500s, 200s, and then make a decision to like whether to keep moving forward and then cut ties with the legacy service. And if something is not working as expected, you could just roll back as well. You could decrease the amount of workloads in Kubernetes and go back to that legacy infrastructure. So you could have the ability, to like roll back. And this is what the Envoy primitive gives us. Since everything is running Envoy, we could just send the configuration, convert the configuration data from the two different infrastructures and send it out to the sidecar envoys that they understand. So with that plan, those 3 goals were achieved, right? It's one, the product engineers don't need to change any code, or networking code to make this happen. They just use the Envoy client, say what service they want to talk to, and Envoy knows how to route that traffic to which IP address. We have a way to incrementally roll out. The product engineer could slowly increase the workloads in Kubernetes or decrease it if things are not going well, and that way you have you have the ability to roll back, fix what you need to fix, and start all over again.
All right, so we're done with the migration, right? So we did all the hard work, and you might think we're done. But really, if we stop there, we're missing out on perhaps the most important part of this framework, which is sitting back and looking at what we did and running a retrospective so that we distill the lessons that we learned in order to improve as engineers and bring those lessons to our next migration so that we're not repeating the same mistakes over and over and over again. So now we want to give an overview of the lessons that we learned with this particular migration. The first one is that when you're moving systems from a legacy system to a new system, you want to provide semantic parity across both versions. And this is essential if one of the goals is to provide a transparent rollout for product engineers. You don't want to have one system behave different from the other from the perspective of the product engineers, because if you do that, then you're adding cognitive load to how they're doing things. Secondly, semantic parity allows us to actually run this migration as we have a live system. Like Lita said, Lyft is a system that cannot take downtime. We can't just turn it off and say, hey, we're under maintenance, we'll come back in a couple months. We'd lose our business. So I equate this to the golden egg problem. It's kind of like when Indiana Jones is in the cave and he's trying to remove the golden egg and put the rock. Although here you're hopefully doing it in the reverse order, and you leave a golden egg so that other engineers enjoy your infrastructure. The second lesson that we learned in this framework is we really need to be aware of the trade-offs that we're making. It's impossible to optimize a system for all different aspects of the features that you want to provide. So you really need to make decisions about where you're going to optimize and where you're going to cut corners. In particular, for this migration, we had to have trade-offs in the consistency model. And Envoy is designing an eventual consistency model. This means that at any given timestamp of the system, different pieces of this largely complex and distributed system might have different state and different understanding of where the system is. This makes for easier to implement systems. However, as you're migrating things with an eventual consistency model, there's longer tails of convergence. That means that behavior takes time to actually converge to the desired end state. This might make it hard for the engineers that are doing the migration to actually reason if the end state is actually working. And so this is why it's very important to be able to observe your system correctly.
So what was really great about the fact that we have that network primitive Envoy running everywhere, we got this unified observability. So what that means is that like Envoy emits a lot of stats, network stats. So it emits latency the same way, the count of 500s, 400s, and the amount of traffic each service is getting. So what was really nice is to be able to compare apples to apples, and that way we could deduce if the migrations was working as expected. Because again, in the Kubernetes world, like you get different stats from AWS. So it's really nice to have that one piece of that observability where it's like the same, so that you could compare apples to apples to ensure that things are working as expected. However, there were moments in the migration where we did not have the necessary observability, such that like we didn't tag IP addresses as what was Kubernetes and what was legacy, and that was really hard to debug. And at that moment in time, we were not afraid to just pause the migration, put in the necessary observability that we needed in order to fix the discrepancies that we were seeing, and then roll that out, and then figure out what the bug was, fix it, and then start the migration again. So you cannot, I think the biggest lesson here is also do not be afraid to stop your migration and ensure that you're not flying blind, because that would be the worst case scenario, is like you think everything is working, but secretly, silently, things are becoming unreliable and unstable, and that is not a situation you want to be in. So we made it a point to be comfortable, not to pause and stop the migration, and make the necessary fixes and add the necessary observability to ensure that things are correct. Lastly is we wanted to ensure that we have enough protection to be enough safeguards and kill switches so that if the migration was going away, like we could turn those on or like use those tools so that we could de-risk ourselves. So one way was the fact that we are able to scale down Kubernetes and still send traffic to the legacy services, legacy infrastructure, and be able to still keep Lyft healthy in that way. The other way is we could have also failed health checks. So if Kubernetes was going awry, we could fail health checks on the Kubernetes workloads, and that could immediately stop traffic going to those pods. And we also placed kill switches as well, and we also ensured that we tested those because you don't want to be in a situation where you place kill switches and when you want to use them in an incident, they're not working as you thought or as expected. That is not a situation you want to be in. So placing the proper protections so that you de-risk your migration is very essential.
So today's case study has been about how Lyft migrated to Kubernetes, and more specifically, how we as the network team were able to use the tools that we had at our disposal to make that migration more seamless and transparent for service owners. But what we really want you to take away from our talk is this framework that we are using to do our migrations. First, we need to understand the why we're even expending all of this energy and all of this technical resources to go through this migration. We need to justify that with business reasons that are actually helping the business, and at the same time, not damaging the business. So we can really skimp on reliability. Second, we need to think about the how we're actually going to do this migration. Not only what the end state looks like, but also what are the tools that we have at our disposal, and what are the tools that we need to build to ensure that this migration is successful. What is the current state of the system? What are the historical trade-offs that we've made that are now guiding us to go to this new version of our infrastructure? And lastly, what are the goals that we're trying to achieve with this migration? What are the things that we're going to optimize for in our new system that are actually going to go back to that justification that we made in the first step? And obviously, and most important, once we're done with the work, we need to go back and analyze and do a retrospective of how this work will inform the next migration, because this is how we really grow as engineers. So with that, thank you very much.